Today we're going to be covering 8.3 arcs of a circle. So let's go ahead and begin with a little bit of a definition. Our first definition will be consisting of an arc. An arc consists of 2 points on a circle and all the points on the circle needing to connect the points by path. Now, again, both these points will be on the circle itself, so they're going to be on the edge, on this curved part. And then for the arc, it's just going to be those 2 points and then all the points in between. So it's going to end up looking something like this. Now, a simplified version of an arc for the definition can just be a portion of the edge of a circle. So as we can see, we have this arc here. It's just a portion of the edge. And honestly, an arc can consist of the entire thing, or almost all of the entire thing, or up to almost nothing. An arc can be as big or as small as you want it to be. Just depends on the problem itself. So there's a couple different types of arcs, and they're all closely related to something called the central angle. So let's go ahead and begin with that definition. So here we have a circle. Let's go ahead and name this circle Circle O. And again, it's called Circle O because point O is the center of the circle. So that's why it gets the name Circle O. Now, if I draw a central angle from here, a central angle is always formed at the center of our circle. That's how it gets the name central angle. And that's a very important term to remember. Central angles are going to be used quite often. So anytime that you have an angle that's being formed with the center of your circle, that is called the central angle. So I'm going to go ahead and draw one here. Here's my central angle. I'll call it theta. And it's created by ray OA and ray OB. So there's a couple different names that I can give this angle. I can either give it angle theta, or I can give it angle AOB. Both of those are central angles. So whenever you run into these, you'll notice, hey, this is a central angle because it's formed at the center of the circle. And again, naming convention-wise, you can either name it with the 3 letters, or you can name it based upon the angle name within the center. I don't want to just call this angle O, because angle O can be signifying the larger angle on the outside as well. The other definition that we have here is a minor arc. A minor arc is an arc whose endpoints are on or between the sides of a central angle. It is less than 180 degrees, so that's very important for us. It needs to be smaller than 180 degrees, or smaller than half the circle. So a full circle is 360 degrees. Half a circle is 180 degrees. So it needs to be less than 180 degrees, and it's named by 2 letters, making it a short path. So in this case, if I have points A and B that are on my circle, I would have minor arc AB. Now, when we name arcs, we're always going to draw an arc above it, just signify that we're dealing with an arc of a circle, rather than a segment or a line or anything like that. Just draw an arc above it, just signify an arc. Again, it's a minor arc. Some important things about minor arcs is that it needs to be less than 180 degrees, less than half a circle. And then also the naming conventions are important, just like everything else in geometry. The first letter is our starting point. The second letter is our ending point, and also the direction that we want to go. Since this is a minor arc, we want the shortest path, which means I'm going straight from A right over to B. You may be thinking, well, I can go from A all the way around to B, but that wouldn't be less than 180 degrees. That'd be more than half the circle. And further, we want the shortest path, so we want to go straight from point A right over to point B, so no breaks. So again, first letter is our starting point. The second letter is the direction that we'll go. The last super important part of these is that the central angle is related to the arc that it's facing. So what we call this arc is it's the intercepted arc. And it gets the name of intercepted arc because OA is intersecting the circle, OB is intersecting the circle, and the intercepted arc is the arc that's in between those intersections. So anytime that we have a central angle, it will always have the same measure of openness, the same degree measure as our minor arc. So therefore I can say that theta, the degree amount of theta, is equal to the degree amount of arc AB. meaning the central angle's degree amount is always equal to the arc measure's degree amount. And again, we're talking about we're talking about measures of openness, meaning angles, meaning degrees, and once we get there, radians. So again, these will always be equal to each other in terms of degree amount. And that's a very important concept for us. Now, as you saw earlier, we had a black point, point A up here, and it just modeled the way that we would draw our arcs when we're naming these. So it started at A, and you saw it travel towards B. So you're going to see that quite a few times today, just showing you the pathway that you take when you're drawing up these arcs. So the next definition that we have is a major arc. A major arc is an arc whose endpoints lie outside of the central angle, meaning it must be a larger angle than 180 degrees. It needs to be bigger than half the circle. Major arcs are named by 3 letters instead of 2. And that's a very important piece here. So I'm going to go ahead and draw a major arc, arc CUD. Arc CUD is a major arc. And again, we know that because it travels past half the circle, and it's using 3 letters. So some important things with major arcs. Again, it needs to be greater than 180 degrees, and the 3 letters is a big giveaway. The 3 letters is very important because that deals with our naming conventions once again. So it's saying that we start at point C, our first letter. The direction that we travel around the circle is towards point U. And then lastly, we go through U and we end up at point D as our final point. So that's how we're always going to be naming these. The first letter is where we start. The second letter is the direction that we go. And the third letter is where we end. So start at point C, move through point U, and end at point D. So this point will show the pathway that we would take for this arc. So again, we have this big black point at point C. It's going to take the path that we would travel to show arc CUD. So it would start at point C, it would go through point U, and end at point D. Just to make sure that we have naming down, we're going to go ahead and go through a couple examples here. So here's the difference in naming. I'm going to have 2 different arcs, arc AE and arc ACE. Again, the second letter is always showing the direction that we're going. So for our first arc, arc AE, we're going to go ahead and start at point A, our first letter. Second letter is going to be our direction that we travel, and if there's only 2 letters, that's also where we end. So I start at point A, and then I travel towards point E, and since there's only 2 letters, I also end at point E. As for arc ACE, again, we're going to start at our first letter, so I start at A. I move towards point C, so I'm traveling around the circle towards point C first, and then then I'll end at E. Let's see what happens if I travel this direction. Well, I start at A, I travel towards C, and I need to end up at E. So you can see that I'd actually go around 1.5 times, which we don't want. We shouldn't fully go around a circle with these. So therefore, I did that wrong. I shouldn't go around this direction, but rather I start at A, I then move towards C, and I must end at E. If I go around the circle more than one single time, I went the wrong way. So let's see this path. Start at A, go towards C, and then end at point E. That's the difference in naming, and that's very important when you're dealing with arcs, and they tell you an arc. You need to know what arc they're talking about. So just keep that in mind. First letter is starting point, second letter is direction, last letter is endpoint. First letter is starting point, second letter is direction, last letter is endpoint. So just keep that in mind as you guys try these out. All right, the last definition that we have for our arcs is a semicircle. A semicircle is just half a circle. It measures 180 degrees. So of course we have our center here, and we have segment AB that we can draw going through that center. It's half a circle. And since we have this line segment here, line segment AB, I know that's going to be equal to 180 degrees. Now further, anytime that we have a semicircle, that segment that I can create, that chord AB here, that will always go through the center, which would make it a diameter. And that's something that always occurs whenever we're dealing with semicircles. All right, let's go ahead and use all the information that we just learned in order to solve a couple problems. So here we go. Find the measure of each arc of circle R. So the first one that we have is arc MN. So if I look here, we start at M, we end at N. There's 2 letters, so we want the shortest path. So it'd just be this minor arc here. Now, looking at this, we already have the central angle that maps with this minor arc. The central angle being 80 degrees. And if we recall, the central angle is always equal to the intercepted arc. Therefore, arc MN is equal to 80 degrees. Next, we have arc MPN. So this time we have 3 letters. That means that's probably going to be a major arc. And then our second letter is telling us direction. So I start at M, our first letter. I travel towards P, and then I end at N. So it's this full arc here. Now, I know that there's 360 degrees in a full circle. I'm not traveling the full circle though. I'm traveling all the way except these last 80 degrees here in blue. So therefore I can do for arc MPN, this arc here, this red arc, I'll call it theta. I can go ahead and say that it's a full 360 degrees minus the green 80 degrees that we have. Well, 360 degrees minus 80 degrees will give us 260 degrees. Or sorry, 280 degrees, my bad. A little brain fart there. Then lastly, we have arc PMN. Again, 3 letters, meaning that it's probably going to be a major arc. Let's go ahead and check it. Start at point P, travel through M, and then end at point N. So P to M to N. So just this arc here. Now if I look at this arc and I draw it up, I can tell that it is creating a straight line. And I can see that with line NP. And I know that in a straight line, there's always going to be 180 degrees. So that'll be the measurement of arc PMN, 180 degrees. All right, now, next up, let's go ahead and focus in on the difference between the amount of openness, the angle measure, and the length of our arc. So, arcs are only congruent whenever they have the same central angle, the same angle measure, and the circle needs to have either the same radius or they need to be part of the same circle. So what I'm going to do here is I'm going to go ahead and draw a central angle. So I have my central angle as angle A, center B, or 65 degrees here. And as we can see, this creates a couple different arcs on our circle. So we have 2 different arcs. I have arc CD and arc AB. Those are our 2 intercepted arcs. Now, in this picture, we can see that the measures of the arcs are the same. They're both equal to 65 degrees. We can see that right in the center here. However, those arcs are going to have different lengths. They're going to have different distances across. Obviously, we can see that AB is a longer distance than CD is. So those arc lengths will be different, but the amount of openness of the arcs, the angle measure, will remain the same. So again, if we have different radius lengths, that will imply that we have different arc lengths. And on top of that, it's very important that we see that the measure, the length of arc CD is less than the length of arc AB. So the lengths are different, but the angle measure is the same. For these 2 arcs to be equal to each other, they would have either had to have been on the same circle, or they would have had to have the same radius. So the radii would have had to have been the same as well. So those are the only two options. So again, even if they have the same angle measure, that does not necessarily mean that they have the same distance in terms of arc length. All right, let's go ahead and talk about some circle theorems dealing with our central angles, our intercepted arcs, and chords. Now, we have 6 theorems here. They're all going to be very closely related, and after we go through them, you're going to see them all connect. So here it goes. Our first theorem states, if 2 central angles of a circle, or congruent circles, are congruent, then their intercepted arcs are also congruent. So I'm going to go ahead and draw 2 central angles in my circle. I have angle SOT, and I have angle AOP. If these 2 red angles are congruent at the center, then by this theorem, the intercepted arcs are congruent. So if angle SOT is congruent to angle AOP, that implies arc ST is congruent to arc AP. That's all this theorem states. If the central angles are congruent, then the intercepted arcs are congruent. Now, for theorem 80, it's just saying the converse of this. They're just switching the if-then portions of this theorem. So they're saying that if the arcs are congruent, if ST is congruent to AP, if you see this on your circle, then you'll know that the central angles are congruent as well. So it's just the converse of it. If arc ST is congruent to arc AP, then angle SOT is congruent to angle AOP. That's all this circle theorem is stating. Let's go ahead and move on to our next one. Very similar. It says if 2 central angles of a circle are congruent, or of congruent circles, then their corresponding chords are congruent. So now if we have 2 angles in the center of our circle that are congruent, let's go ahead and draw those. I have angle AGN and angle LGE. So these 2 red angles, if they're congruent, then the chords that are created by their intersections of the circle, so we can see that they intersect the circle at all these points, the chords that I can create from those intersections would be congruent. So if angle AGN is congruent to angle LGE, then segment AN is congruent to segment LE. Theorem 82 right below is just the converse of this. It's just saying the opposite. It's saying that if segment AN is congruent to segment LE, then the central angles would be congruent. Then angle AGN would be congruent to angle LGE. That is our second circle theorem, because again, these are just the same theorems, just converses. And then we have our final 2. And this really connects all of them together. The final theorem that we have states, if 2 arcs of a circle or of congruent circles are congruent, then the corresponding chords are congruent. So if I have 2 arcs on my circle, arc OH and arc ES, if these are congruent, then the chords are congruent. Then segment OH would be congruent to segment ES. We can see that in our picture now. Theorem 84 is just the converse. Converse would be if the chords are congruent, then the intercepted arcs are congruent. So again, it's just the converse of it. It's saying that if OH is congruent to ES, then arc OH is congruent to arc ES. All right, let's go ahead and tie all these theorems together because they're all pretty much the same. They're all saying the same thing. And that really ties together with this. Congruent arcs, chords, and central angles all go together. And here's the theorems that we've just been covering. And you notice that we have 2 blanks now. It says, if 2 blank of a circle or congruent circles are congruent, then their blanks are congruent. Now, you're going to go ahead and take these blanks and you can replace them with either central angles, arcs, or chords. And it will work for any of them. So if the minor arc is congruent, if minor arcs are congruent, then central angles are. If chords are congruent, then central angles and minor arcs are. Central angles are congruent, then both chords and minor arcs are. So they're all interrelated. And that's what works for this. It makes it very simple for us to use those theorems. Because if you see a minor arc congruent to another minor arc, and you see chords attached, chords are congruent. Central angles are congruent. It allows you to do so much information with these. So let's go ahead and use these theorems and all the material that we've learned so far to prove some theorems. So here's our first proof of the day. Given circle O and B is the midpoint of arc AC, we'd like to prove that triangle ACD is isosceles. So to get started, we always start with our given information, circle O and B is the midpoint of AC. That's given to us. And then I'm going to go ahead and use information from statement 1 to further this proof. So statement 1, they just tell me that I have a midpoint of an arc. So that means that B is right in the middle of this arc. Well, if B is in the middle, that means that AB should be the same as BC. Because if something's in the middle, it's splitting it perfectly in half. So arc AB is congruent to arc CB. And the reason I can say that is the definition of a midpoint. The midpoint of an arc divides the arc into two congruent arcs. That's the definition of a midpoint. Usually we use it with segments, but it works with arcs as well. Now, we just went through a lot of theorems, and we now have two congruent arcs. And we know that if the arcs are congruent, then either the chords, we don't have any chords, then either the chords or the central angles, what we're actually going to focus on, are congruent. So I have some central angles here that map up with these intersected these intersected arcs. So therefore I can say that angle AOB, this angle right here, well this matches with this arc, and angle BOC matches with this arc. So therefore I can say that angle AOB is congruent to angle COB. The reason we can say that is because if two arcs are congruent, then the corresponding central angles are congruent. If two arcs are congruent, then corresponding central angles are congruent. Next up, we have angle AOB already. Now, it is congruent to another angle on the circle. That would be angle COD. And the reason I can say that these two angles are congruent is because they're vertical angles. So I can say angle AOB is congruent to angle COD because the vertical angles are congruent. You can also say vertical angle theorem. That works just fine as well. I can do the same exact thing with angle COB and angle DOA. Those are also vertical angles, so they would also be congruent to each other. Now, if AOB is congruent to angle COB, and these two angles in green are congruent, these two angles in red are congruent, well then I should be able to say that angle AOD is congruent to angle COD. And the reason I can say that is through the transitive property. If all these things are congruent to each other, then they're congruent through the transitive property. I'm just skipping all this congruency in steps 3 through 5 here. Now at this point, now that I know that those two angles are congruent, well, what types of angles are they? Well, they're formed at the center of our circle, so they're central angles. And I know that if central angles are congruent, then corresponding chords are congruent, and corresponding arcs are congruent. Well, which one will help me further this proof, to prove that ACD is isosceles? That would be the chords. So I'm going to go ahead and say that DA is congruent to DC. And the reason that we can say that is because if two central angles are congruent, then the corresponding chords are congruent. It's one of those theorems that we talked about earlier today. We can finally end this proof now, because looking at this triangle ADC, I see that we have at least two legs that are congruent to each other, which by definition makes that triangle isosceles. So we can finally say that triangle ACD is isosceles. And the reason that we can say that, it's the definition of an isosceles triangle, but you can also say that if two legs of a triangle are congruent, by definition, that triangle is isosceles. And with that, this proof is complete. Let's go ahead and move on to our next one. Our next proof, we have circle O. We're also given that triangle ABC is isosceles with base CB. We would like to prove that arc ABC is congruent to arc ACB. So to get started here, we always start with our given, circle O, an isosceles triangle ABC with base BC. It's given to us. Next, well, if I have an isosceles triangle, that means that we have two congruent legs. And if CB is the base, that means that AC must be congruent to AB. Because that is a definition of an isosceles triangle. If a triangle is isosceles, then at least two legs are congruent. Oh, well, if I look at these two legs, they're both chords, right? They both have endpoints on the circle, making them a chord. And I know that if we have two congruent chords, then the central angles are congruent, but we don't have central angles here. But we also know that if we have two congruent chords, that the intercepted arcs are congruent, and we can use that. So I can now say that arc AC is congruent to arc AB. And the reason for that is because if chords are congruent, then the corresponding arcs are congruent. Is there anything that's shared? Because again, we're trying to prove that arc ABC is congruent to arc ACB. So is there anything that both those arcs share? Well, yes. They both share arc CB. So since it's on both arcs, I can go ahead and say that arc CB is congruent to itself. And of course, anytime that something is congruent to itself, that's always going to be by the reflexive property. Lastly, well, what would happen if we see that we have two red congruent arcs, we have a green congruent arc. If I add the red congruent arc with the green congruent arc, and I do that same thing with the other one, the red congruent arc and the green congruent arc, well, those end results should still be congruent because I'm adding congruent pieces together. And if that's the case, then I can say that arc ACB is congruent to arc ABC, which is exactly what we're trying to prove here. And the reason I can say that these arcs are congruent is all I'm doing is I'm adding the red and the green arcs. So that would be the addition property. And with that, this proof is now complete. All right, let's go ahead and try out our sample problem and end this video up. So here's our final problem of the day. We're given that AB is congruent to CB. We have AB is equal to 25x plus 85, and BC is equal to 30x plus 90. We want to find the measure of arc AEC. So getting started here, first off, if I know that that the chords are congruent, then I can say that the arcs are congruent. So arc AB is congruent to arc BC. If two things are congruent, we can set them equal to each other. 25x plus 85 equals 30x plus 90. So I'm just setting those two equal. From here, I solve for x. I'm going to subtract 25x from both sides, subtract 90 from both sides. That'll leave me with negative 5 equals 5x. From here, if I want to solve for x, I divide both sides by 5, leaving me with x equals negative 1. At this point, I want to go ahead and plug back in to our original. And again, since A, B, and BC are the same, it doesn't matter which one I plug into. I'll get the same answer regardless. So plugging back in for AB, I'll be left with arc AB, which is equal to arc BC, because again, they're congruent, is equal to 25 times negative 1 plus 85. Well, 25 times negative 1, that's negative 25, plus 85 is 60, so arc AB is 60 degrees. And if arc AB is 60 degrees, that means that arc BC is also 60 degrees, because they're congruent to each other. And at this point, we should be able to find arc AEC, because if there's a full 360 degrees in a circle, we're already using up 120 for arc AC, so therefore 360 minus 120 will give us arc AEC. Let's go ahead and enter that into our calculator. 360 minus 120 will give us 240 degrees. And that is our final answer. Thank you guys so much for watching today. If you have any questions,